First, let me remind you that the kinetic friction force is the part of the contact force that appears when two solid objects are sliding against each other. The contact force also includes a normal force perpendicular to the surfaces touching, while the friction force is parallel to those surfaces. In the previous lecture, it was briefly mentioned that the direction of the kinetic friction force is in opposition to the sliding. But what does it mean to be in opposition to the sliding? Let us take two objects that are touching. The surfaces touching are shown to be horizontal, but this is not a requirement, as we had seen with the example of the book being held against a wall. Let us assume that we make two markings on the objects and that at t equals 0, both markings are aligned. After a time delta t, during which sliding occurred, the two objects might have slid into this configuration. The red marking is now to the right of the left marking. If you choose the blue marking on object 2 as the origin of a reference frame, the displacement of the red marking would look like this. Let delta d12 be the displacement of object 1 in respect to object 2. Similarly, you could choose the red marking as the origin of a different reference frame and create a vector displacement delta d21 to explain the motion of object 2 in respect to object 1. These two vector displacements are in opposite direction to each other, and they define the direction of the sliding of each object. The kinetic friction force exerted by object 2 on object 1 is in the opposite direction to the sliding of object 1. So here, Fk1 is pointing to the left. Similarly, the kinetic friction force exerted by object 1 on object 2 is in the opposite direction to the sliding of object 2. Fk2 is pointing towards the right. Fk1 and Fk2 are pointing in opposite directions to each other, as they should according to Newton's third law. Note that those displacements only involve the relative position of the two objects. There was no mention of which object was moving in respect to another reference frame, such as the ground. Now that we have dealt with the direction of the kinetic friction force, let us pay attention to its magnitude. According to Newton's third law, the force exerted by object 1 on object 2 is equal in magnitude but opposite in direction to the force exerted by object 2 on object 1. It implies that the magnitude of the kinetic friction forces are equal to each other. However, this law does not give any hint about the numerical value of the kinetic friction force. We have to turn our attention to experimentation. It is found that the magnitude of the kinetic friction force is proportional to the magnitude of the normal force, and the constant of proportionality is the coefficient of kinetic friction, mu k. This relationship might give you an impression of déjà vu, but it is different from the equation Fs max equal to mu s times Fn that gave us a way to evaluate the upper limit of the range of values for the static friction force. The only resemblance is that they both involve the magnitude of the normal force. Mu k has a different value from us. It is smaller for a given combination of material. It still depends on the two materials of the surfaces that are touching. Here is an example of coefficient values for a wooden object in contact with a wooden floor. The fact that the coefficient of kinetic friction is smaller than the coefficient of static friction for the same combination of material means that a greater applied force is required to start an object sliding, starting from rest, than the applied force required to keep the object sliding at a constant velocity once it is sliding. Now let let us apply those concepts to numerical problems. This example involves an object that is originally at rest before an applied force is suddenly exerted. We are interested in getting the values of the acceleration and the friction force after the onset of this applied force. So here is our wooden floor and the wooden crate of mass m. The free body diagram before the applied force is exerted involves the gravitational force and the normal force. There is no need for a friction force at this stage, but once the applied force is in place, either a kinetic or static friction will appear depending on whether a sliding occurs or not. Either way, the friction force will be in the opposite direction to the applied force, because if it is a static friction force, it would need to be equal in magnitude and opposite in direction to the applied force to ensure that there is no motion, i.e., no sliding. If the friction force is kinetic, the sliding would be in the same direction as the applied force, and the friction force would oppose that. Let us use this set of reference directions. The list of givens includes the mass of the crate, the coefficient of static friction, the coefficient of kinetic friction, the magnitude of the applied force. To this, we can add the fact that the crate is at rest initially, and that the motion is strictly horizontal, if there is motion at all, so there is no acceleration in the vertical. Regardless of which type of friction is involved, the vertical component of the net force is 0, because the vertical component of the acceleration is 0. And F net y is the sum of the y component of the normal and the y component of the gravitational force. Looking at the free body diagram and knowing that the magnitude of the gravitational force is mg leads to this, and it implies this equality. Now let us assume that this is a case of static friction. Let's see where it leads us. In order for no sliding to occur, the crate must stay still in respect to the floor, so it must not have a velocity in respect to the floor, so no acceleration, meaning also no net force. We start with this value for the net force. We next express the component of the next force in terms of the forces with the next component, and eventually in terms of the magnitude of these forces. This last equation implies that the magnitude of the applied force is equal to the magnitude of the static friction. You might think that we are nearly done and that the acceleration is 0 and that the friction is equal to 64 Newton towards the west. But there is something to do first, and it is to check if this value of the friction force is within the possible range. We need the static friction to be smaller or equal to its upper limit, recalling that Fs max is mu s Fn gives this. Using the results from the evaluation of the two components of the net force leads to this. Substituting the givens gives this, and the use of a calculator gives this, which is not possible. The applied force is too strong for the static friction to be able to stop the sliding. So we have come to the conclusion that sliding will occur and that we are dealing with a kinetic friction force. The magnitude of the kinetic friction force is given by this relationship. Using the result from the balance of forces in the vertical gives this. Substituting the givens leads to this expression, and the use of a calculator gives the magnitude of the kinetic friction force to be 24 Newton. Now on to the task of evaluating the acceleration. We start with Newton's second law expressed for the x component. We have the same type of forces involved as before, except that the friction force is kinetic. Expressing the x component of the forces using the magnitude of the forces leads to this. We can now use the relationship of the magnitude of the kinetic friction force in terms of the other variables that we have derived earlier. Next step is to isolate for the acceleration, followed by substituting the numerical values for the givens, and the use of a calculator to arrive at a numerical value of 3.4 meters per second squared for the x component of the acceleration. The final answers are that the acceleration is 3.4 meters per second squared towards the east, and that the kinetic friction force is 24 Newton towards the west. This example is to address the difficulties arising when not all forces involved have only one non-zero component. Here the motion is horizontal, but the force of tension has an horizontal and a vertical component. We are looking for the magnitude of the force of tension. In short, we are looking for the tension. As usual, let us start with a free body diagram. Here is the flat horizontal ground and the sleigh of mass m. It is being pulled by a rope, making an angle theta with the horizontal. The force of gravity is exerted on the sleigh, as well as a normal force perpendicular to the surfaces touching. Without friction, the only horizontal force is the horizontal part of the force of tension, so the sliding would be to the right. The kinetic friction force would oppose that and point to the left. We will use the following reference directions. Our givens are the mass of the sleigh, the angle that the rope makes with the horizontal, the coefficient of kinetic friction, and because the sleigh has a constant velocity, the acceleration is 0. Before we start working with Newton's second law, let us use trigonometry to set up expressions for the two components of the tension force. We create a right-angled triangle with the magnitude of Ft as the hypotenuse. The other sides are proportional to the magnitude of the x and y components of the tension force. Cos theta involves the ratio of the adjacent side and the hypotenuse. And because of our choice of reference directions, the x component of the tension force is positive, which leads to this. Sin theta involves the ratio of the opposite side and the hypotenuse. And because of our choice of reference directions, the y component of the tension force is positive. We can remove the absolute value and get this. We are now ready to use Newton's second law, taking into account that both components of the acceleration are 0. For the y components, we have three contributions: the gravitational force, the normal force, and the vertical part of the tension force. Replacing them with expression for these components gives this, and isolating for the magnitude of the normal force gives this. Notice that the magnitude of the normal force is smaller than the weight. It received help from the tension force in its opposition to the weight. Next is to work with Newton's second law for the x components. Substituting expression for these x components of forces gives this. Now it is time to use the relationship of proportionality between Fk and Fn, followed by using the equation for the magnitude of the normal force found earlier. We're almost there. All that is left is a bit of algebra. Written here is the last equation from the previous slide. We want to isolate for Ft. The first thing to do is to collect the terms with Ft together on one side of the equation and leave the rest for the other side. Next, we can factor out Ft, which allows us a way to isolate Ft. We now reach the stage where the numerical values of the given can be substituted, and the use of a calculator leads to a numerical answer of 15 Newton. This is our final answer. Now that we have studied many examples of the use of Newton's second law with a variety of forces, it is time to look at examples that illustrate the difference between external and internal forces. This will be the subject of the next installment.